Okay, Algebra 1, we are starting our last unit. So today we're talking about systems of equations. When I use the word systems, what I mean is I've got more than one. So we've done a graphs of equations of lines. A system of equations when you would be when you have multiple lines and you're looking for a solution to both of those. We'll introduce it starting with a graph, and then we'll talk about other methods we use to solve these systems. So let's look at this example. Juan and Leo were supposed to meet and drive ATVs on a trail together. Juan is late, so Leo started without him. Okay, so Leo started his trip at 5 miles an hour. Sometime later, Juan starts, and hopefully they will meet at the end of the trail. Okay, so if we look at this, so Leo starts first, Juan is second. So if we look at what Leo is doing, Leo is going 5 miles an hour. So when I see a question like this and I see that's my rate, I'm thinking distance equals rate times time. That equation is probably going to be underlying what's going on here. So if I want to write an equation for Leo's distance from the starting point, well, that would be the rate times however much time he went. Well, if he rode for X hours and we know his rate was 5 miles per hour, then we know that for Leo, this equation, what y equals 5x, at any point in time would tell me how far he has driven. Okay, so if I look at graphing that, so 5x, so this is my time in hours, and this is my distance in miles. So I know that there's a 40-mile trail, so I won't be able to go I'm not going to be able to do the entire thing here, but I know that his rate is 5. So if I look at what is happening with Leo, he starts here, okay, and for every hour he goes 5 miles, okay, so that means the rate is 5 over 1, okay, and so forth. So I can see this is what's happening in his ride. Now what I want to do in this unit, you have to be very careful with precision of lines because we're looking for solutions from our graph. So I'm doing this virtually, but you should have a straight edge that you can line up all of these points, okay? Now I know that Juan starts later, X hours later. So if Leo is on the ATV for X hours, okay, if Juan starts later, he starts H hours later, what is his time? So his time in the ATV is going to be X minus H. And we know he's going at a rate of what, 8 miles an hour? So the equation for him is going to be y equals 8 times X minus H. Okay. Now, I really can't graph that right now because I could graph 8x, but 8x minus h, that's going to change the y-intercept, and I don't know what h is. But I know the slopes of both of these lines. So let's look a little bit further. Let's figure out, if we graph them together, how much of a head start Leo must have to finish at the same time as Juan. Okay, so if I look at their starting point, okay, so Leo's starting point, he starts at, starting at 0, ending at 40 miles, okay? So he's starting at 0, 0. And we know that if he's going, what, 5 miles an hour? And he's going to go for 40 miles, okay? So if we look at his distance equals his rate times his time, 40 miles is equal to 5 times his time. So his time is going to be 8 hours. Okay. So he's going to end at the point 8:40. Okay. His speed is what? 5 miles per hour. So the equation for this guy, the slope is what? 5. So it's just going to be y equals 5x. Now I know, let's just go ahead and graph this guy. So I want to try to, when you have a blank grid like this, you want to figure out how to scale it so you can fill up the grid. The last thing I want to do is to graph it right here and waste all of this space. So I know that it's taking, what, 8 hours for him to do this. So how can I divide this up? So 1, 2, 3, 4, let's do it this way. So if this is 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, 6, 7, and 8 hours, okay? And this is my time in hours. And then the distance, we know the distance is 40 miles. So it looks like if I do, what, 10, 20, 30, and 40. So my goal is to try to scale it so that I can fill up the grid. The last thing I want to do is go 10, 20, 30, 40 and just use that part of the graph. Your graph is going to be much more inaccurate if you try to scrunch it down to a small size. So I know that for Leo, it's just y equals 8x. So that's going through the point 0, 0. And if the slope is 8, 2, 4, 6, 8 over 1. Okay. 2, 4, 6, 8 over another 1. 2, 4, 2, 4, 6, 8 over 1. 2, 4, 6, 8 over 1. 2, 2, 4, 6, 8 over 1. Sorry, backed up. That was not Leo. Leo was what? 5x. Sorry about that. So 5x was his speed. So if I redo that, it's you go up 5. So 2, 4, so it's 5 over 1, which is right there. And then if I go up another 5, I go over there. Okay. What I can do, if I go up 5 over 1, that's the same as going up 10 and then over 2. Okay. Up 10 over 2, up 10 over 2. So if I draw that line, there, try to make this about as accurate as I can. It should be good. Okay. So this is what Leo is doing. And he ends at the point 8:40. Okay, so going 5 miles an hour, it takes him 8 hours to get to the end of the trail. Now, we know that Juan starts later. What we do know about Juan is he's going to have to end up at the same spot. We want them to meet at the same spot, and he's going 8 miles per hour. Okay. And so we've got to figure out the equation here, or we can just go to the graph. Okay, I know he has a slope of 8. So if I look at Juan's trajectory, he's got to end here, but the slope is 8. So 2, 4, 6, 8 over 1 right there. Okay, so he's going to have to end at the same spot. 2, 4, 6, 8 over 1. 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 So if I look at this and I connect those points, right there. Now the question was, we know that 1 starts later, so 1 is y equals 8 x minus h. In order for him to end at the same spot, he has to start 3 hours later, okay? So we look at the total time. Leo is riding that bike for 8 hours, and Juan is riding his bike from 3 to 8 for 5 hours, okay? So the point is, I was able to use a graph before I knew the equation, okay? So this equation is going to be y equals 8 x minus 3. So y is equal to 8x minus 24, okay? So this is an example of using a graph. Now, when we do this, this is called solving a system of equations by graphing. What you want to do, you want to graph both equations. You want to find the point of intersection, if there is one on both lines, then that is a solution to both equations. If it truly is a solution to both equations, it should solve both equations, and I can check it. So let's look, for example, in this one. So here is my x-axis, here's my y. The first one, negative 2x minus 4. So I'm going to graph that one in blue. So if I go down to negative 4, the slope is negative 2. So if I go down 2 over 1, now what I want you to do, I want you to fill in as much of this grid as you can with these points, because this helps you not only draw us a line, but also know the points of intersection. Okay. So try to fill up as much of the grid as you can with the lines. Then I'm going to draw the line. Like so. And this line has arrows on both ends. Okay. And it's always good if you label the line, this is y equals negative 2x minus 4. When you've got multiple lines on a graph, it's always helpful to know which one is which. Now let's graph the next one. It has a y-intercept of 6, and the slope is 1/2, so up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, down 1 over 2, down 1. Did I do that right? Oh wait, sorry, I messed that up. Down 1 over 2, down 1 over 2, right there. So I can see by filling up this grid with points, I believe I have found the solution. Okay, so then if I draw this line, right there, this is the line y equals 1/2 x plus 6. So it appears that the solution is what? Negative 4, 4. Now that's what it appears like from the graph. How do I know it's not negative 4.1 or negative 4.02? I can plug this into both equations. So if I plug it into the first equation, you get 4 equals negative 2 times negative 4 minus 4. So that's 8 minus 4, which is 4. That checks out. Plug it into the bottom equation, you'll get 4 equals 1/2 negative 4 plus 6. This is 6 minus 2, which is 4. That is the correct solution. Okay. So what I've done is just graphically verify. I've graphically found the solution and algebraically verified it. Same thing here, just, okay, graph these as carefully as I can. Y equals 2x plus 10. The slope is 2. So if I go down 2 over 1, over 1, over 1. So these points will help me draw a line, which you know should be straight. Okay. And if I do this line, right there. So this is y equals 2x plus 10. Y equals negative 1/4 x plus 1. So y-intercept is 1. If the slope is negative 1/4, I go up 1 over 4. There's my intersection. Up 1 over 1, 2, 3, 4. Okay. Down 1 over 4. Down 1 over 4, and so forth. So then I can draw that line like so. This is y equals negative 1/4 x plus 1. It appears that the solution there is what? Negative 4/2. I can verify that. If I check it with the first equation, I get 2 equals 2 negative 4 plus 10. So that's 10 minus 8, which is 2. That checks out. In the second equation, 2 equals negative 1/4, negative 4 plus 1. So that is 1 plus 1, which is 2. So that is my solution. Let's try this one now. Those were in slope-intercept form. You can do it where like, okay, I can put it in slope-intercept form and graph it, or I could graph it from standard form. It doesn't matter. Let's take the first one and let's just put it in slope-intercept form. So what is it? 5y equals negative 15, x plus 25. Divide everything by 5, and you get y equals negative 3x plus 5. So negative 3x plus 5, slope is negative 3. And draw that line with your straight edge. So this is y equals negative 3x plus 5. The next one is y equals, if you look at it, that's the same thing, right? This next line is y equals negative 3x plus 5. So it is the same line. So if I were to go draw that, I mean, clearly I'm going to see, if I draw that line, come on. I need to try to get rid of that other piece there. There we go. So, made a mistake. Let's draw that line now. Insert shape line. That line starts right here, and it basically is the same line. Five minus 3x. So I don't have one point of intersection, okay? So the solution, what points, so that this is what points satisfy both equations? Or what are all the points that are solutions to the equation? Well, any point on that line will work, okay? So there are infinitely many solutions. Now I can tell you right up front, 5, 5, that point is not a solution. I know it's not a solution because it doesn't lie on the line. It has to be a point on the line, okay? How many points are on that line? They're infinite. So it doesn't mean the answer is any number in the world. It means there are infinitely many solutions, but they all lie on that line, okay? So that's one thing that can happen. So the previous two problems, they intersected at one point. Here, they were identical. Let's look at what happens here. Y minus 2x equals 6. So this is y equals 2x plus 6. So go to 6, do a slope of 2. Okay, and connect the dots. So this is y equals 2x plus 6. This equation is 2y equals 4x plus 8. Divide everything by 2. Y equals 2x plus 4. And let's do this guy in red. Y equals 2x plus 4. So right there, slope of 2. Connect the dots. And we get something like this. So this is y equals 2x plus 4. Now, what points satisfy both equations? These lines are parallel, they never intersect. There's never going to be a point that lives on both of these lines. So there is no solution here. So these are the three things that can happen when you're doing a system of equations with lines. They intersect at one unique point. They are identical lines, in which case you have infinitely many solutions, or they never intersect and there's no solution. So if I look at this, if I have one solution, that means they intersect at one point. What do you know about the slopes of these two lines if they intersect? Well, I know that these lines have different slopes. There's no way they intersect. If they have the same slope, they're parallel and they never intersect. So if I look at the case where there's no solution, these lines have the same slope. What about the y-intercept? Can they have the same slope and the same y-intercept? Well, that happens right here. These have the same slope and the same y-intercept. That makes them identical. Here, in the middle case, they have the same slope, but they have different y-intercepts. In the case where they intersect, these two lines happen to intersect at the y-intercept, okay? So they do have the same y-intercept, but that's not necessarily the case because look at the problems we did earlier. These lines intersect, but they have different y-intercepts. So there's nothing definitive I can say. When they intersect at one point, all I know is they have different slopes. They could or could not have the same y-intercept. But I know if there's no solution, they got the same slope and a different y-intercept. If they're the infinitely many solutions, same slope, same y-intercept, okay? What if we can't definitively determine a condition from the graph? Let's look and see what's going on here. 2x minus 3, so go to negative 3 and do a slope of 2. And again, I'm filling in as much as I can to make this line as accurate as I can because my solution, it depends on the accuracy of my graph. Y equals 2x minus 3, and then y equals negative 5x plus 6. So slope is negative 5. So you go down 5 over 1. Down 5, 1, 2, 3, 4, 5 over 1. Up 5, right there over 1. 1, 2, 3, 4, 5 over 1. So clearly by doing the dot, I can see I could not see dots hitting on the line. It didn't land on the grid point. If I draw this line, like so, I can see the lines intersecting. It's clear that there is a solution. But I don't know what it is. Okay, so there is a solution here, but it doesn't appear to land on one of the grid points. Okay, so you can't always, so graphing doesn't always work. Now it works to tell me there is an intersection. I know that for a fact. I know that it's something between, it looks like a number between 2 and 3 for x and a number between 0 and negative 1 for y, okay? But I don't know. So graphically is not going to be the best answer here. So we'll talk about in the future lessons other methods we have algebraically to get to an answer there. Let's look at another word problem example. Monisha and 4 of her friends want to attend a concert. They are trying to decide whether to buy tickets online in advance at the ticket booth or on the day of the concert. They have $360 to buy tickets. Online tickets are $55 each with one $30 charge added to order as a service fee. Tickets at the door are $60 each. For what number of tickets will the cost be the same between the two methods? Okay. Typically, people use X and Y. I mean, I could use, what I don't want to use is O for online. And, this one, it doesn't feel, easy to do non-X or non-Y. So just pick something for one. Um, so what I'm going to do here is pick um, Y to be like the total cost, and X is my number of tickets. So Y is my cost in dollars, and X is my number of tickets. Now, how do I know to pick that? Well, the cost depends on the number of tickets, okay? So you basically determine how many tickets you get, and that's going to make your cost, okay? So two equations I have. In the first situation, the cost is going to be what? $55 for every ticket plus a $30 charge. And so this is the online option. And the other option is to pay at the door, and that's just $60 each. So Y equals 60X. So let's graph these, okay? So if I look at my graph, I'll make that a little bit smaller. X is going to be the number of tickets that I'm purchasing, okay? So I know that with 360, if I just look at this, trying to determine how to scale the axis, $360, that's going to be about 6 tickets, okay? So I want to try to, I don't want to do 1, 2, 3, 4, 5, 6 and then stop here. So I can spread things out a little bit. So I'm going to do, we'll just say 1, 2, 3, 4, 5, 6 to try to spread out. This is the number of tickets. My cost, okay, so the cost has to go up to 360. So if I do 1, 2, 3, I can do this, say 100, 200, 300, 400. Okay. Now, in the first situation with this online ticket, there's a $30 charge, okay? So this is what, 20, 40, 60, 80. So at 0, when you plug in a 0 for X, there's still that one-time charge of $30. So 10, these would be 20, and 30 would be about right there, okay? Then if I look at that, so the slope is 55. So if I look at, I'm sitting there at 0, 30. If the slope is 55, that means if I go up 55, okay, then I'm going to go over 1. So 30 plus 55 is 85. So 85, so 20, 40, 60, 80, somewhere right here, okay, I'm getting this to happen, okay. If we look and just see, let's find another point. What would happen if I buy, say, like 4 tickets? So 55 plus 4, or 4 times 55, that's what, 220? Plus 30 is 250. So at 4, 250, 10, 20, 20, 30, 20, 40, 60, so about right there, okay. So I can see what's going on there, okay. Let's just go further out, like if I had 6 times 55, that's 330 plus 30, that is 360. So 6, 360, so 2, 4, 6, right there, okay. So let's go ahead and draw that line. So right there. So this is my online, Y equals 55X plus 30. Now, in the tickets that are at the door, I'm just paying, it's $60 for each ticket. So at 0 tickets, I pay nothing. 1 ticket, I pay $60. 2 tickets, I'm at 120. 3 tickets, I'm at 180. 4 tickets, I'm at 240. 5 tickets, I'm at 300. And then 6 tickets, I'm at 360. Okay, so if I look at that line, something like that. Now, the question is, when were these costs the same? You can see that the cost was the same right here. Because if you plug a 6 into both of those equations, you get to 6, 360. Okay, so at 6 tickets, the cost is 360 either way. Okay, which method is cheaper? Okay, so if you look at it, it depends. Okay, it is cheaper. If you look at it, the red line is cheaper for for tickets up to 60. Let's look at what's happening at 5. At 5, you get what, 300 in the red line, and if you plug in a 5 there, what is that? 5 times 55, 275 plus 30. That's what, 305. So this one, the blue line, is still higher. So I can see if you look at it, the blue line is more expensive until you get to 60, but they're going to cross there at 60. So they're going to cross, okay? And then once they cross, the red line is going to be there. So which method is cheaper? So the online for less than 6, but it's at the door for more than 6. And how do I know that? Because anytime two lines intersect, the line that was on the top before the intersection point becomes the line on the bottom after that. Which method is cheaper if 20 people are going? 20 people is way over here. So we know that the red line is cheaper, but once they cross, the red line is going to be more expensive. The blue line will be cheaper. So cheaper will be online for 20 people. Okay. So again, this is fairly straightforward in terms of plotting the line, but this is where the line is embedded in a word problem and you're getting the solution from there. So a little bit more involved to get that scenario all worked out. And that leads us up into homework for this section.